welcome to Chemistry Unit 3 on chemical bonds. This is 3.1. Today we're talking about valence electrons, dot diagrams, oxidation numbers, you will need your periodic table, and the types of bonds, ionic and covalent. There will be a handout that goes with the ionic. Please be sure that you have that so that you can fill that in correctly. First, let's talk about valence electrons. Valence electrons are the number of electrons in the outer energy level, and they're the electrons that are involved in bonding. They're loosely associated with the group number, and we've already added those to our periodic table. Dot diagrams are used to show the valence electrons with the symbol. So hydrogen, remember, is in group 1, has 1 valence. And nitrogen is in group 15, has a valence of 5. And remember, those can be in any little groups of 2. Then we get oxidation numbers. Now this is a new thing. Oxidation numbers are the number of electrons that an element would like to gain or lose to complete its outer valence shell. All atoms and compounds want to have a complete outer shell, and 8 electrons, also called an octet, will complete any outer shell. And these come from the valence electrons. So on your periodic table, you already have the group numbers and the period numbers. We also then added the valence numbers, and we circled those. But now we're going to add the oxidation numbers. So, above the valence number, above your circled number, for group 1, put a 1 plus. For group 2, put a 2 plus. Groups 3 through 12 should have positive Rn oxidation. Positive Rn oxidation. Group 13 is 3 plus. Group 14 is 4 plus or minus. Group 15 is 3 minus. Group 16 is 2 minus. Group 17 is 1 minus. And group 18 is 0. Now, oxidation numbers come from the valence. So if you didn't catch that, valences 1 through 3 want to lose their electrons in order to become stable. That's why they're positive. Valences of 5 through 7 want to gain their electrons to become stable. That's why they're negative. A valence of 4 can go either way. So think of it this way. Hydrogen, lithium, and sodium have oxidation numbers of 1 positive because they have a valence of 1. They would really like to give that extra electron away in order to be stable. While fluorine, chlorine, and bromine, they all have oxidations of 1 negative because they have valences of 7. They want to gain 1 electron to make their perfect octet of 8 electrons in their valence shell. Now let's look at the types of bonds. There are ionic bonds, where electrons are lost and gained between atoms. It occurs mainly between metals and nonmetals, and it will use the oxidation numbers. Covalent is the second kind of bond that we will study. It is where the electrons are shared between the atoms, and it occurs between 2 nonmetals. You, however, have to be given the number of each element to use because we're not going to go that in depth with covalent bonds. For bonding purposes, remember that beautiful little stair-step line? All of the elements to the right of the stair-step are considered non-metal for bonding purposes. And all of the elements to the left of the stair-step are considered metal for bonding purposes. So, within ionic, you have 4 different kinds of ionic. You have perfect, where the oxidations cancel out. You have no subscripts. You have a crisscross method that will be used to uses the oxidation numbers to become subscripts. You have transition that also uses the crisscross method, and polyatomic that use the crisscross method. And then finally we'll talk about covalent. So these are examples of perfect ionic compounds. Sodium and chlorine. Sodium has an oxidation of 1 positive, chlorine has an oxidation of 1 negative. They combine to make NaCl. Potassium and bromine, again, potassium is a 1 positive, bromine is a 1 negative. They combine to make KBr. Magnesium and oxygen, magnesium is a 2 positive, oxygen is a 2 negative. They become MgO. And calcium and sulfur, calcium is a 2 positive, sulfur is a 2 negative. They combine to become CaS. These are examples of perfect ionic compounds. Crisscross ionic compounds are when they're not perfect, like combining hydrogen and oxygen. Hydrogen has an oxidation of 1 positive, oxygen has an oxidation of 2 negative. The oxidation numbers crisscross, but we lose the sign, meaning positive or negative, when they do. So the 2 negative comes down as a 2, the 1 positive comes down as a 1, and we're left with H2O, meaning 2 hydrogen will combine with 1 oxygen. Again, calcium and chlorine. Calcium is a 2 positive, chlorine is a 1 negative. 2 comes down, 1 comes down, and we're left with CaCl2. 1 calcium combining with 2 chlorine. Transition elements are elements that get their name because they have a variable oxidation. Remember, they had no valence. And I told you to write positive Rn oxidation. Their oxidation is always going to be positive, and you have to be told or given the transition element's oxidation number with a Roman numeral. They will bond ionically and use that crisscross method. So here's some examples of transition ionic. If we wanted to combine copper 1 and oxygen, that would mean that copper had an oxidation of 1 positive and oxygen had an oxidation of 2 negative. They would crisscross, making Cu2O. Similarly, iron 3 and chlorine. Iron 3 is Fe3 positive, chlorine Cl1 negative. Those oxidations would crisscross, making FeCl3. Finally, we get into ionic with polyatomics. Ionic compounds that are pre-formed with unique names, charges, and oxidations. They can and will ionically bond again with other compounds and elements. So it's a multiple bond, that's why it's called a polyatomic. Be sure that you have the handout for the next few slides. You're having to write the names or complete the formulas for the most common polyatomics. These will be attached to your formula sheet. So polyoxidation 1 negative, you have acetate, bicarbonate, chlorate, cyanide, hydroxide, nitrate, and nitrite. The formula for acetate is C2H3O2. Bicarbonate is HCO3. Chlorate is ClO3. Cyanide is Cn. Hydroxide is OH. Nitrate is NO3. And nitrite is NO2. All of these have an oxidation of 1 negative, so they will act like group 17 elements. Oxidations of 2 negative are carbonate, chromate, peroxide, sulfate, sulfite, and silicate. Carbonate is CO3. Chromate is CrO4. Peroxide is O2. Sulfate is SO4, sulfite is SO3, and silicate is SiO3. All of these have oxidations of 2 negative and will act like group 16 on the periodic table. Okay, so there is a group of polyatomics that have other oxidations. So an oxidation of 3 negative is phosphate. Oxidations of 1 positive are ammonium and hydronium. And oxidations of 0 are ammonia and methane. The formula for phosphate is PO4. Ammonium is NH4. Hydronium is H3O. Ammonia is NH3. And methane is CH4. These are some polyatomic examples. If I wanted to combine aluminum, which was Al3 positive, with sulfate, SO4 2 negative, remember that the 4 is part of the sulfate, so you have to keep it together. The oxidations would crisscross, and notice I've used parentheses, and this would be read Al2 SO4 3. Potassium with nitrate. Potassium is a 1 positive, nitrate is a 1 negative, making KNO3. Ammonium and chlorine is NH4, which is a 1 positive, Cl, which is a 1 negative, makes NH4Cl. And ammonium and nitrate, because polyatomics can bond to each other, as long as you have the right combinations, will make NH4NO3. Now this is really important. In the final answer, if the subscripts match, we leave them off. However, if we keep the subscripts, like Mg2O2, where they match, we make a molecular formula. But if we take them off, it's called an empirical formula. Notice that in ionic bonds, the positive oxidation always comes first, and you have to pay very, very close attention to capitalization, lowercase, placement of the subscripts, and parentheses whenever necessary. Finally, let's look at covalent. Covalent is where they share, and this is simply writing down. There's no process here. If I wanted to combine 1 carbon and 1 oxygen, I would just write CO. 1 carbon and 2 oxygen would be CO2. And 1 phosphorus and 3 chlorine would be PCl3. No crisscross, no muss, no fuss. All right, we're going to be doing lots in class. Thanks for watching.